Alright, hello everybody. So today we're going to talk about improper integrals. So I'll say here, since we started doing integrals, we've assumed that our functions don't have any infinite discontinuities. Okay. But I'll say here, however, it is possible to integrate some functions that do have such discontinuities. These integrals are called improper integrals. Okay. So today we're dealing with these things that are called improper integrals. And we're going to have two types of improper integrals that we're going to talk about today. So the first part of today's video is going to be about type 1, which are going to be infinite integrals. And by that I mean integrals where one of the bounds or one of the limits is actually infinity instead of a number. Okay, so let's say consider f of x equals 1 over x squared for 1 is less than or equal to x. Okay, so let's draw what this region looks like. So we know the graph of 1 over x squared is going to look something like this. Looks something like that, and it goes on towards infinity. So it goes on infinitely in that direction. And we know this point is at x value 1. Okay. And let's say here, this is the function y equals 1 over x squared. And whenever we're calculating the integral, remember the integral is the area under the function. So it's this area here under the function. And we're asking what the area under this function is. So it looks like it might be infinite, because it goes off infinitely in that direction. But we have to check whether that's actually the answer. So I'll say here, since the region under the curve goes from 1 to infinity, it seems like the integral from 1 to infinity of 1 over x squared dx should be infinite. Right, that's just kind of what it looks like. But we have to check whether that's true. So let's see what happens when we take the area from 1 to some number t, right? So instead of taking the integral from 1 to infinity, let's just say we're taking the integral from 1 to just some number t. So the area under the curve between 1 and some number t. So let's just calculate what this is going to be. So our integral from 1 to t of 1 over x squared dx. Right, if we take the integral of this, this is the integral from 1 to t of x to the negative 2 dx. And if we take the integral, we need to add 1 to that number. So we're going to get x to the negative 1 over negative 1 from 1 to t. And I'll rewrite that as as 1 over negative 1 over x from 1 to t. And then we plug in our numbers, 1 and t. And what we're going to get is going to be that this is 1 minus 1 over t. So that's our answer, is 1 minus 1 over t. Okay, so you look at your answer there, and the answer is that this area is actually less than 1. Right, so the area between 1 and just any number you pick out here, the area under the curve is going to be less than 1. So I'll say here, so the above area might be less than 1, right? So we said from 1 to any number that we pick, it's the area under the curve is less than 1, but we don't know what happens whenever we go to infinity, instead of just going to some random number. So the next thing we need to look at is now let t go to infinity. We find the limit as t goes to infinity. Sorry, I miswrote this. The limit as t goes to infinity of whatever our answer was, which is 1 over 1 minus t. And if t is going to infinity here, then this limit is 1. So we can write, and we write. So if we take our integral, so the integral we cared about was the integral from 1 to infinity of 1 over x squared dx. We can rewrite this as the limit as t goes to infinity of the integral from 1 to t of 1 over x squared dx. And we said this thing on the inside, we already calculated, that was this. So this is the limit as t goes to infinity of 1 minus 1 over 2. And we already calculated what that was. That's 1. So it turns out that the area under this graph, this whole area, is actually just equal to 1. So it looks like the area should be infinity, but actually the area is 1. So that's why it's important to actually do the calculation here. So the way we deal with these infinite integrals is we take out the infinity and say, replace it with t, and just take the limit as t goes to infinity, right? So that's our strategy, is just to just replace this infinity with a t and take the limit as t goes to infinity. Okay, so I will go ahead and write down a definition that we need to use right here. Okay. So definition. So part A is going to say if the integral from a to t of f of x dx exists, for all t greater than or equal to a, then the integral from a to infinity of f of x dx is equal to the limit as t goes to infinity of the integral from 1 to t of f of x dx, if the limit exists. And here I'll say, whenever we're doing stuff in this section, we're going to slightly alter the meaning of exists. So I'll say here, exists means the limit is finite. Right? So for everything that we're doing in this section, this is a very important thing to remember. Whenever we say exists in this section, we just mean that the limit, we mean, of course, that it exists, but also, more strictly, that the limit's also finite. So it's saying if this integral it exists and it's finite for all of these values, then this integral is equal to this limit of this other integral, as long as this limit exists and is finite. Okay, so that's part A. Part B is very similar. Part B is going to say if the integral from t to b exists for all t less than or equal to b, then the integral from negative infinity to b of f of x dx equals, let me just rewrite this down here. What I meant to say is the integral from negative infinity to t of f of x dx equals the limit as t goes to negative infinity of the integral from t to b of f of x dx. If the limit exists, which means, of course, that it's finite. Right. So whenever we have these integrals with either the infinity or the negative infinity, we can use this to rewrite our integral with this limit in front. And that actually helps us to be able to solve the integral. Okay. And let's write down a definition. Definition: the improper integrals the integral from a to infinity of f of x dx and the integral from negative infinity to b of f of x dx are called convergent if the corresponding limit exists and divergent if the corresponding limit does not exist. Right. So these are just two new words that we're defining here. We'll say that this integral converges or is convergent if that limit here exists, and we'll say that the integral is divergent if this limit here does not exist, meaning it either doesn't exist or it's not finite. So if the limit here is infinite, then we'll say that it's divergent. Okay. So our question here is going to be, what can you say about the integral from negative infinity to infinity of f of x dx if I tell you both integral from a to infinity of f of x dx and the integral from negative infinity to a of f of x dx are convergent. Okay, so if both of these two are convergent, well, we can try adding them, right? So if both of these are finite and they exist, then we can just try adding them, and that should actually give us this integral here. So this was part A and part B of our definition, and part C, let me write down part C, was the last part, part C, is going to say if both the integral from a to infinity of f of x dx and the integral from negative infinity to a of f of x dx are convergent, then the integral from negative infinity to infinity of f of x dx equals the integral from negative infinity to a of f of x dx plus the integral from a to infinity of f of x dx, where a can be any number. Right, so if we know that this is convergent and we know that this is convergent, and these two are both just some numbers, we can add the numbers to get what this should be. Okay. Now let's try to do some examples to try to see whether some integrals are actually convergent or divergent. So let's do example number 1. Alright, so example number 1 is going to say determine whether the integral, so this is the integral from 1 to infinity of 1 over x dx, is convergent or divergent. Right, so we need to figure out whether this is infinite or if it's just equal to some number. Okay, so let's write down, we've got our integral from 1 to infinity of 1 over x dx. And we said our strategy for these problems is to take out this infinite sign and replace it with a t. So we're going to rewrite this as the limit as t goes to infinity of the integral from 1 to t of 1 over x dx. Right, so that's our strategy. That's what we said we would do for these problems. Okay. Now, we can take this integral, this is the limit as t goes to infinity, of the integral of 1 over x is, of course, just natural log of the absolute value of x. And this is going from 1 to t, so we just plug in these things. So we're going to get the limit as t goes to infinity of, this would be the natural log of t minus the natural log of 1. Right, and the natural log of 1, that's saying e to what power gives me 1. This is actually 0. Okay, and now we're taking the limit as t goes to infinity of the natural log of t, but if you think about the graph of the natural log, or you just think about what's happening here, this is the graph of natural log, and it goes infinitely off in this direction. So this is actually going to get infinitely big. So your answer here is going to be infinity. So the integral of this thing is saying there's actually an infinite amount of area under this graph between 1 and infinity. So this is infinity. And you can ask yourself, does that mean it's convergent or divergent? And if you look at our definitions here, we said it exists when it's finite, and it does not exist when it's infinite. So here it's divergent if the limit does not exist. So this is divergent. So the integral from 1 to infinity of 1 over x dx diverges, aka the area under the curve tends towards infinity. Okay, so let's just draw two functions. I'm going to draw two functions here. So the first function I'm going to draw is going to be 1 over x squared. So this is our function f of x equals 1 over x squared. And let's also draw the function 1 over x. Right, so it essentially looks the same, it's just a little bit less steep. So this is g of x equals 1 over x. And what we're doing is we're computing the area under, so for the blue graph, this is the area, right? That's the area under 1 over x squared. And for the red graph, it's actually this whole area under the red graph. So we see the area under the red graph is a bit bigger than the area under the blue graph. And we said that the area under this blue graph is actually just 1, and the area under the red graph is infinity. So that's where the difference is. Okay. So let's talk about example number 2. So example number 2 says evaluate the integral from 0 to infinity of x e to the minus x squared dx. Okay. So again, we said our strategy was to get rid of that infinity sign and replace it with a t. So this is equal to the limit as t goes to infinity of the integral from 0 to t of x e to the minus x squared dx. Okay. And now we have to think about how do we solve this integral. So we can't really rearrange it anyway. So thinking about what we did in the last section, we saw, well, whenever we're just trying to solve an integral, our next step is to try to solve it using u substitution. So let's go ahead and try to use u substitution. Here our inside function would be our minus x squared. So let's say u equals minus x squared. Okay. Then you take the derivative of both sides. Du is minus 2x dx. But up here we have x dx, not minus 2x dx. So I'll divide by negative 2 on both sides. We get negative 1/2 du is x dx. And now we can rewrite this integral using u substitution. Okay. So we keep that limit out in front. We got the limit as t goes to infinity of the integral of, this becomes e to the power of u, and this x dx gets replaced with negative 1/2 du. And we can factor out our negative 1/2, both from the integral and from the limit. So this is negative 1/2 times the limit as t goes to infinity of, sorry, this was from 0. Okay, well, we have to choose whether we're changing the limits or not. That's something I forgot to mention. So let's just rewrite the limits also in terms of u. That's something I forgot to do. So if we go ahead and, let me use that. So you don't have to do this, but if you don't do this, then you're going to have to replace what u was back before you plug in the numbers. So I'm just going to replace these in terms of u. So this was 0, and we plug it into our u. So u of 0 is going to be equal to negative 0 squared, which is 0, and then u of t is going to be negative t squared. So this is from u equals 0 to u equals negative t squared. Okay. And now we can take our integral. Let me just rewrite what we had here. And now we can just take our integral. So this is negative 1/2 times the limit as, limit as t goes to infinity of e to the u. The integral of e to the u is just e to the u. Evaluated from, to write u equals 0 to u equals negative t squared. So now we can just plug these in for u. And if we do that, we're going to get negative 1/2 times the limit as t goes to infinity of e to the negative t squared minus e to the 0. E to the 0, that's just 1. And then e to the minus t squared, let's consider what that is. We can rewrite this as negative 1/2 limit as t goes to infinity of 1 over e to the t squared minus e to the 0 is 1. Okay, so that says, this is a bit hard to read, but that's 1 over e to the t squared. Okay. And then now we have to consider, well, t is going towards infinity, so what's happening to this fraction? What's happening to this fraction here? And if you look at it, well, this fraction, this denominator is getting infinitely big, so this fraction is going towards 0. So this goes towards 0. And then now you're just multiplying negative 1 times negative 1/2. And if you do that, you get the answer, which is positive 1/2. So that's the answer for this problem. So I actually just worked out the whole thing doing the u substitution, but if you do all of the steps, this is where you get, and your answer should be 1/2. So it turns out that this integral is convergent, and the answer is 1/2. Okay. Now let's do one more example. before we move on to the next part of this section. Okay, so example. So we're going to have the integral from 1 to infinity of x squared plus x plus 1 over x to the 4th dx. So remember, the first step in solving integrals is to try to algebraically simplify the thing. So we can try to use algebra to simplify this. And the way I would do that is to just break this up into this one fraction into 3 fractions. So this is the integral from 1 to infinity of 1 over x squared plus 1 over x cubed plus 1 over x to the 4th. Right, because you get x squared over x to the 4th, that's 1 over x squared. X over x to the 4th, that's 1 over x cubed. 1 over x to the 4th, that's here, dx. Okay. But we said our strategy for this section was to replace this infinity sign with a t. So I'll go ahead and rewrite this as the limit as t goes to infinity of the integral from 1 to t of 1 over x squared plus 1 over x cubed plus 1 over x to the 4th dx. And now we need to take our integral. Well, let's actually rewrite our integral first, is what I meant to say. So 1 over x squared, that's the same thing as x to the negative 2. This is x to the negative 3. This is x to the negative 4 dx. Now we can take our integral. So this is the limit as t goes to infinity of, this would be x to the negative 1 over negative 1 plus x to the negative 2 over negative 2 plus x to the negative 3 over negative 3, evaluated from 1 to 2. Okay. And if you write out what all of these are, this is the limit as t goes to infinity of, so this one becomes negative 1 over x. This one becomes, sorry, this should be minus 1 over 2 x squared minus 1 over 3x cubed from 1 to 2. Okay, so now we first plug in t, then we subtract when we plug in 1. So we're going to get limit as t goes to infinity of, this would be, so first you're going to have minus 1 over t minus 1 over 2t squared minus 1 over 3t cubed. And then you're going to subtract whenever you plug in 1. So minus 1 over 1 minus 1 over 2 minus 1 over 3. Right. So next step is to analyze what's happening. And notice t is going to infinity, so all these fractions are going to 0 because they have t in the denominator. So this whole part is going to go away. This whole part is going to go to 0. Then you're just left with this. So you've got, this is just going to be, this would be 1 minus 1/2 minus 1/3. Right? So that's the same thing as 1/2 minus 1/3, which is the same thing as, so multiply both sides of this by 3, you get 3/6 minus, multiply both sides of this by 2, 2/6, and here this is 1/6. So this is our final answer. We just found the final answer. Okay. So again, the only thing to worry about with these problems is just replacing this infinity sign with a t, and then writing the limit as t goes to infinity. That's the main thing with these problems. Okay. So we're going to talk about now our second type of problem in this section. So we talked about improper integrals of type 1. Now we're going to talk about improper integrals of type 2. Which is going to be discontinuous intervals. Okay. Right, so the second type of discontinuous integral, the second type of improper integral is the discontinuous integral. So we can ask the question, how do we calculate the integral from a to b of f of x dx when f of x has a vertical asymptote at b. Right, so if we draw a picture of what's happening, we've got our numbers a and b, and we've got our function. So remember, we've got a horizontal asymptote at b. So our function is going to look something like this. Where it's going up towards infinity at this vertical asymptote, and we're trying to compute the area. This color's going out. We're trying to compute the area under this graph between a and b, where there's that vertical asymptote. So let's write down a definition. So part A, if f is continuous on the interval from a to b and is and discontinuous at b, then the integral from a to b of f of x dx equals the limit as t goes towards b from the left of the integral from a to t of f of x dx if the limit exists. In other words, the limit is finite. Right, so our strategy is to, instead of saying that we have the integral from a to b, we're replacing that b with a t, and we're taking the limit as t goes towards b. And we're going to do the same thing from the other direction. So part b is going to say if f is continuous on the interval from a to b. Remember, this is the interval not including a, because there's a parentheses at a, and discontinuous at a, then the integral from a to b f of x dx equals the limit as t goes towards a from the right of the integral from t to b of f of x dx if the limit exists, meaning is finite. Right. So our strategy is to just, if we have a discontinuity on the end of the interval, we just replace that letter. So here it was the interval from a to b. We replace b with a t, and take the limit as t goes towards b. So that's our strategy. And again, we'll say that the limits are convergent if they're finite and they're divergent if the limit is infinite, right? And one last thing, part C is going to say if f has a discontinuity discontinuity at C where A is less than C is less than B, and both the integral from A to C of f of x dx and the integral from C to B of f of x dx are convergent, then we'll write the integral from A to B of f of x dx. You can kind of guess what we're going to write here. This is the integral from A to C of f of x dx plus the integral from C to B of f of x dx. Right? So if we've got some kind of discontinuity in the middle, we'll just break it up into two intervals like that. Okay, so let's go through an example. So example number 3 is going to say we have the integral from 2 to 5 of 1 over the square root of x minus 2 dx. So we have to analyze whether there's any vertical asymptotes inside of there. And remember, a vertical asymptote occurs when the denominator is 0. So we have to think about when the denominator is 0, and if this denominator is equal to 0, that means x is equal to 2. So I'll ask the question, where is f of x equals 1 over square root of x minus 2 discontinuous? And our answer is at x equals 2, so we'll use part B. Right, so part B tells us how to deal with if this bottom side here of the limit is actually, or if our function is discontinuous at this number. It tells us just replace that with a t. So that's what we'll do. So we'll go ahead and rewrite this. So we can rewrite this as limit as t goes towards 2 from the right of the integral from t to 5 of 1 over root x minus 2 dx. Okay. So here we would do a u substitution to solve this, setting u equal to x minus 2. I'm going to skip that for now, but I encourage you to fill in the steps there, but we're eventually going to get the limit as t goes to 2 from the right of 2 square root of x minus 2 of this thing evaluated from t to 5. Right, so that's eventually where we're going to get to, and this is equal to limit as t goes towards 2 from the right of, so we just plug in the numbers, right? So we plug in 5, so we're going to get 2 root 3, minus whenever we plug in t, we get 2 root of t minus 2. Okay, so that's what happens whenever we plug in these limits. And then you analyze, well, what happens if t is going towards 2? Well, then this part here is going towards 0, so you just look at the first part. So our answer here is 2 square root of 3. So that's how we deal with that type of problem. Alright, so our fourth example is evaluate this integral if possible. So the first thing to try to look for is whether there's any discontinuities inside of this interval for this function. So if you look at this function, you'd say, well, if you tried plugging in 1, you're going to be dividing by 0, so it's discontinuous there. So we'll say here f of x is discontinuous at x equals 1. So use part C, right? Because in part C we said if we've got a discontinuity somewhere between A and B, we just break up this integral into these two parts. So that's what we're going to do. Okay. So let's write down our original integral. And we said we're going to break that into two parts. The integral from 0 to 1 of 1 over x minus 1 dx plus the integral from 1 to 3 of 1 over x minus 1 dx. Okay. So we can break it into these two parts. And now we can just look at each part. So I'll just look at one of these two parts. I'll look at this first integral. So we're going to try to solve this first integral. So we're going to write down here the integral from 0 to 1 of 1 over x minus 1 dx. Okay, and we're going to try to solve this integral. Notice it's not continuous at 1, so we need to use what we said in part A, which was to replace this 1 with a t. We're going to write the limit as t goes towards 1 from the left of the integral from 0 to t of 1 over x minus 1 dx. Okay. And now you would do u substitution to solve this integral, but what you're going to get is the limit as t goes to negative 1, or sorry, not negative 1, as t goes to 1 from the left of the natural log of the absolute value of x minus 1. This is evaluated from 0 to t, and then you just plug in your numbers, right? So you plug in t and you plug in 0. You're going to get the limit as t goes to 1 from the left of the natural log of the absolute value of t minus 1 minus the natural log of the absolute value of negative 1. Now, natural log of 1, that's saying what power do I have to raise e to get 1? That is 0. So this part here, this is 0, so we can get rid of that part. And then we look at this part. Now t is going towards 1, so you're approaching the natural log of 0. So let's look at the graph. Let's figure out what's going on from the graph. So I'm going to draw for you the graph of natural log of x. It looks something like this. We drew this earlier. Right? So this is the graph of natural log of x. And notice that whenever you're getting very close to natural log of 0, you're going towards negative infinity. So this part goes towards negative infinity. So your answer here is going to be negative infinity. So the answer here is that this first part of the integral is equal to negative infinity. So since this part diverges, this part also diverges. Or sorry, we don't know if this part diverges or not. But since this part diverges, we can say that the integral diverges because one of its parts diverges. So we can say here, so the integral from 0 to 3 of 1 over x minus 1 dx diverges. And that was because one of its parts diverged. Right, so you just have to break it into these two parts, solve one of the parts, and notice since one of them diverges, we don't have to worry about the other part, we just know the whole integral diverges. Okay, the next thing to talk about is called the comparison theorem. So let's write that down. Okay, so the comparison theorem. So let's say, suppose f and g are continuous functions with f of x is greater than or equal to g of x is greater than or equal to 0 for all x greater than or equal to f. So part A is going to say if the integral from a to infinity of f of x dx is convergent, then, right, so we know that the bigger function, the area under it, the integral rather, is convergent. So if the integral of the bigger function is convergent, then the integral of the smaller function should also be. So the answer here is then the integral of from a to infinity of g of x dx is also convergent. Right? So g of x is a smaller function, so if the bigger one is convergent, then the smaller one is also convergent. And part B is going to be very similar. If the integral from a to infinity of g of x dx is divergent, right? This is the integral of the smaller function. If the integral of the smaller function is divergent, then the integral of the bigger function is definitely also divergent. So then the integral from a to infinity of f of x dx is also divergent. Right, so remember here, you've got two functions. Let's say this is a, and for every number bigger than a, you've got some smaller function, g, and some bigger function, f. Right, so you got the bigger function and the smaller function, and this is just saying how they relate to each other in terms of the area under their graphs. Okay. So this is actually, as simple as this looks, this is actually very useful, a very useful tool to help us solve integrals. So let's say here example number 5, show that the integral from 1 to infinity of e to the negative x squared dx is convergent. Okay, so we're going to try to show that this integral is convergent. And notice this is kind of a difficult problem, right? We don't know how to solve this by u substitution. So I'll say here, since we want to show convergence, we want to find some function bigger than g of x equals e to the negative x squared that we know how to integrate. Right. So we can try to find some function that's bigger than e to the negative x squared that we actually know how to integrate. So let's consider the fact that, well, here we're only worried about x values that are bigger than or equal to 1. So let me write here. So, or let me first just write our guess. Our guess is maybe e to the negative x. That might be a bigger function that we can use. But we need to check that this is actually bigger than e to the negative x squared. So let's start with what we know. So we know that x is greater than or equal to 1 here. We know that that's true. I guess we're going from 1 to infinity. Now if you go ahead and multiply both sides by x, then x squared is bigger than or equal to x. And if you multiply both sides by -1, you've got to flip this inequality. So negative x squared is less than or equal to negative x. And then you just raise e to the power of each side, and you get that e to the negative x squared is less than or equal to e to the negative x. Right? So e to the negative x is actually a bigger function. So if we can show that the bigger function is convergent, the integral of the bigger function is convergent, then the integral of this smaller function would also be convergent. So that's how we're trying to use the comparison test here. Right? We're using part A. If the integral of the bigger function is convergent, then the integral of the smaller function is also. Okay, so that's what we're going to do. So we're going to replace our hard problem with an easier problem. Now we just need to find the integral from 1 to infinity of e to the x dx. Sorry, e to the negative x dx is what I meant to say. Right? And remember, whenever we're trying to find these infinite integrals, we need to replace the infinity with a t. So we need to take the limit as t goes to infinity of the integral from 1 to t of e to the negative x dx. And remember here, you would solve this by letting u equal to negative x. And if you do that, this is going to be the limit as t goes to infinity of negative e to the negative x evaluated from 1 to t. And if you plug in both 1 and t there, then you're going to get the limit as t goes to infinity of, this would be negative e to the negative t plus e to the negative 1. Right? And here you just have to plug in t to be infinity here. So if you plug in t equals infinity, then you're taking e to the negative infinity, which is 1 over e to the infinity. So 1 over an infinitely big number, that's 0. So this thing here, since this is e to the negative infinity, which is the same thing as 1 over e to the infinity, that goes to 0. So you're just left with this part, and your answer is 1 over e. So what we can say here is, since, let me use a different color here. Since e to the negative x squared is less than or equal to e to the negative x for all x greater than or equal to 1, and we solved here that the integral from 1 to infinity of e to the negative x dx is convergent. Since this integral is convergent, we can say we must have that our original integral from 1 to infinity of e to the negative x squared dx is convergent. Right, so that's our answer there. That's how we showed that our original integral is convergent. Okay, so let's do a bit of a recap here. Let me just go ahead and erase this board. Okay, so let's say here comparison test recap. So these are the steps. So step 1 is determine whether you're looking for a function bigger or smaller than your original function. Right? So remember, for the convergence for the comparison theorem is what I meant to say. For the comparison theorem, you're trying to look for part A for a function that is going to be smaller than your original function. So if this was your original integral, and you're looking for one that's bigger. And for part B, this was your original integral, and you're looking for a new function that's smaller. So you need to figure out what you're looking for. That's your first step. All right, so step 2. Verify using algebra or graph knowledge that your comparison function is indeed bigger or smaller than your original function. Right? So remember, we had to check whether our function was actually bigger than our original function. Step 3. So our third step is to compute the integral of the comparison function using the same upper and lower bounds as the original integral. And our last step, step 4, is going to be to interpret your results using the comparison theorem. Right, so this is the checklist of what we're going to do. We're going to do step 1, step 2, then step 3 and 4. Okay. And now I'm just going to do one last example using these steps. So I'm going to have to erase the steps, but we're going to use those steps. Okay. So example number 6, last example, show that the integral from 1 to infinity, this is supposed to be an infinity symbol, from 1 to infinity of 1 plus e to the negative x over x dx is divergent. Okay, first thing, something I forgot to take note of earlier, something that I should have written down. This is actually pretty important. I should have written this down. Let me do that here. So if we have the integral, let me actually do that here. If we have the integral from 1 to infinity of 1 over x to the power of p dx, if we have something like this, then we can say that this converges if p is strictly greater than 1, and we can say that it diverges if p is less than or equal to 1. Okay, so this is actually pretty important because whenever we have this type of integral, we can just instantly say whether it's convergent or divergent. So if this p is greater than 1, meaning it's like 2 or 3 or 4.5 or something like that, then the integral converges. But if this integral, if this number p is less than or equal to 1, remember if it was equal to 1 over x, we said that integral diverged. So this is an important fact that you can use for all the homework problems, but we're going to need that fact to solve this problem. So let's go ahead and, well, let me go back to the problem. So we're trying to show that this is divergent. If we look at the comparison test, we said if the integral of g of x is divergent, then the integral of f of x is also divergent. So if the integral of the smaller one is divergent, then the integral of the bigger one is also divergent. So we need to pick a smaller function that we can show the integral of that is also divergent. Okay, so we're trying to find a smaller function. That's how we figure out that fact, because we're trying to prove that it's divergent. So we're trying to find a smaller function that's divergent, namely what I just mentioned here. Whenever we're taking the integral of 1 over x from 1 to infinity, that's divergent. So looking at this, if we just go ahead and say, well, 1 over x is less than or equal to 1 plus e to the x over x. So we're trying to look for a function that's less than, so this is 1 over x. So that function is indeed less than our original function. And then we can write here the integral from 1 to infinity of 1 over x diverges, dx, diverges because of what I wrote down right here. Therefore, the comparison theorem gives the integral from 1 to infinity of our original function diverges. Right, again, so the way we figure out whether it needs to be smaller or bigger is just by looking at the wording of the theorem and saying, well, if we find a smaller function that diverges, then the bigger function is definitely going to diverge. So it's kind of, you don't have to memorize the theorem, just think about it logically. If a smaller function diverges, then the bigger function definitely diverges. If a bigger function converges, then the smaller function is definitely also going to converge. So that's how you would kind of solve one of those problems.